Today we're going to look at the pressure-temperature relationship of gases. So far we've looked at how pressure and volume are related, that's Boyle's law. Then we looked at Charles' law, which is how volume and temperature are related. And now we're going to kind of do a similar law to Charles' law, but it's going to be how temperature and pressure are related. So to start off, we're going to go back to the kinetic molecular theory because this helps really explain what's going on when we're looking at the pressure-temperature relationship. So if we remember, when you increase the temperature of anything, the kinetic energy of those particles is increasing. They start to move faster. They overcome the forces. They start to spread out. Inside of a container of gas, you're going to have more particles hitting the walls of that container more often. Not only that, they're going to be hitting the walls of the container more often with more force. So that's going to push harder on the outside walls of the container, which increases, in turn, increases the temperature, or increases the pressure. So if you think about gas particles at low temperature, they're zipping around, bumping into each other, bumping into the walls, and then they're pushing with a certain amount of force. The volume or the area of the container is the same. If you increase their speed, again, the area of the container, the walls stay the same, but that force increases. And remember that pressure is a force over an area. So if we think of pressure as force over an area, if we increase force, we make the force big, and we keep the area the same size, then the pressure goes up. So that's basically what's happening. And we can go back to Maxwell-Boltzmann's distribution, where we're looking at the kinetic energy of the particles at different temperatures, and you can see that energy, that average energy is increasing overall, which is increasing the collisions and the force. So Joseph Gay Lussac, he followed Charles's work and Boyle's work, and he investigated this relationship. And the really neat thing about this is he found the same thing that Charles did, that the pressure of the gas is directly related to the temperature. So if you increase temperature, you increase pressure. If you decrease temperature, you decrease pressure. Now, he held the amount of gas constant, just like we have in all of the other laws, but in this case, we're holding the volume of the gas constant. So the container is rigid. It can't expand like the syringe we used for Charles's law lab. So if we graph this relationship, you take his data, we graph it, we would get the exact same, well, not the exact same, but a similar graph to what we did for Charles, just the only difference being that the y-axis is now pressure instead of volume. And if we extrapolate that line, again, remember, extrapolate means extending the line past your data range that you've collected. If we extrapolate that line back to the x-axis where the pressure of the gas would be 0, then there would be absolutely no molecular motion, 0 energy, which means we have absolute 0. And he realized that it's about the same temperature. It's minus 270 degrees Celsius-ish. And as we've done more and more experiments, we've realized, or we've come to terms with, that it's minus 273.15 degrees Celsius. So if we think about it's kind of the same idea as Charles' law. So if we think about the relationship, since it's a direct relationship, we can say that the pressure divided by its temperature will give you a constant value. So no matter what pressure and temperature you have, you're always going to, if you divide those things as a ratio or a fraction, you're going to get a constant value, a number that's always the same. So if P1 divided by T1 equals K and P2 divided by T2 equals the same K, then we can say that P1 over T1 is the same thing as P2 over T2. And again, in all of our gas law problems, we have to have our temperatures in Kelvin because it doesn't work. Like if the Kelvin temperature doubles, then the pressure doubles and the volume would double. But it doesn't work with Celsius, and it also gets messy when you start having negative values. So it's a direct relationship with temperatures being in Kelvin. So we can visualize this relationship, all of these relationships, using kind of a symbolistic or a symbolic kind of system where we can actually take like a piece of wood and drill some holes into it. So if we take 3 holes and we drill it into a piece of wood, 1 hole is pressure, 1 hole is temperature, 1 hole is volume. If we hold one constant, so imagine we put a pin here and we move the board up and down, then if I increase the temperature, then the volume has to pivot with it. So then as temperature increases, volume increases. So if we hold P fixed, pressure fixed, if in other words we keep it constant, volume and temperature move up and down together. they are what we call directly proportional. You can write that as this Greek letter alpha, so T alpha V, that this means directly proportional. Proportional. Now, if we take the same idea, so I'm going to erase what I've done here, take the same idea and we hold the volume fixed. So I put a pin here, and now I increase the temperature, so I make the board go up because I'm heating it up, and that means the pressure is going to go up. So that means they're moving up and down together. So you could imagine that the PT side is going to move up and down together, and it's going to pivot on at the V. So this is also a direct proportion. So we can say pressure and temperature are directly proportional to each other. Temperature is fixed. If we hold that temperature fixed, the pressure and volume act like a seesaw. So if I change what I've done, and I put the pin in the temperature, if I increase the pressure, because it's got a pivot, it's like a teeter-totter, the volume has to drop. So one side goes up, the other side goes down, and vice versa. So this is what we call an inverse proportion. And just a second, do I have it in here? No. So what we would say is that pressure is proportional to 1 over V. So it's an inverse. Inverse, like if you think of inverse sine or x to the power 1, negative 1, that's an inverse. So that's like 1 over x. That's what we call inverse. So 1 over V is inverse. And that symbol just means proportional to or proportionate to. So we're going to just jump right in and do some examples. It's going to look a lot like Charles's law. So we'll do a few different example problems. I'll do one, and you guys can try a couple and see how it goes. So the first one is we have a sealed tank containing argon gas at 18 degrees Celsius and 875 kilopascals. What is the pressure if the temperature changes to 32? So again, I'm going to do the two methods. But before we do anything, we need to get our Celsius temperatures into Kelvin. So 18 degrees Celsius, we add 273, remembering that Kelvin is always better than Celsius. So that ends up being 291, oh, sorry, not 219, 291 Kelvin. And our temperature was 32, the second temperature, so that ends up being 305 Kelvin. I'm just adding 273. So now I'm going to go through, if we're going to do formula method, and I'm going to label all of my things. So we know, I'll write my formula first. So P1 over T1 equals P2 over T2. So I'm starting off at 18 degrees Celsius or 291 Kelvin. So that would be my starting temperature. I'll call that T1. And the pressure at that temperature is 875. So that's not P2, can't write today, P1. Now, what is the pressure? So we're looking for P2 if the temperature changes to 32 degrees Celsius. So that would be T2. So we set this up. I put P1 where it goes, so 875 kilopascals over 291 Kelvin equals P2, we don't know, and 305 Kelvin. So to solve for P2 with this fraction, we need to multiply both sides by 305. So I'm going to do that, and what ends up happening is P2 is going to equal 875 kilopascals times 305 Kelvin divided by 291 Kelvin. And again, like if we need to go back through the algebra, I'm just doing this, 305 Kelvin here, 305 Kelvin here. These two cancel. So what I'm left with is what I've just written. And then our final answer should end up being P2 is equal to 917 kilopascals. So now we need to ask ourselves, does this make sense? So our temperature went up, so our pressure should go up. Those two things are related to each other directly. So the temperature went up from here to here. Now, notice it wasn't a monstrous jump. It was 291 to 305. So in terms of Kelvin jumps, it's not that big of a jump. So our pressure is not going to be jumping super high either. So it's from 875 to 917. That kind of makes sense. It's kind of a proportionate amount. So if we're doing the proportion method or the logic or ratio method, however you want to call it, what we're going to do is we're just going to write exactly what I just said. The temperature is increasing, so that means our pressure needs to increase. So I'm going to start off with my pressure that I have 875 kilopascals. And I'm going to make this number get bigger using the two temperatures. So 305 Kelvin, 305 Kelvin divided by 291 Kelvin. I put the larger number on top so that it makes the pressure go up. And you'll get this exact same value, 917 kilopascals. So I believe the next two are try these ones. So you can give them a try. When we're solving for temperature, you need to make sure, especially if you're doing formula method, that you do your algebra properly. So I'll walk through that after you guys try the question. So give the next two questions a try. Stop the video, pause it, whatever, and then give them a shot, and then come back and check your answers. So for this question, if we're going to actually be solving for temperature. So that makes the algebra a little bit trickier because temperature is going to be in the denominator, right? Temperature is always in the denominator. If we can remember that, we know all three gas laws. So I'll write my formula here anyways if I do formula method. So it's P1 over T1 equals P2 over T2. So we start off with 97 kilopascals at 22 degrees Celsius, and it survives this fire. Let's see, if the tank is able to withstand a maximum pressure of 350, what is the maximum temperature? So first things first, always need to change our temperatures to Kelvin. So that's what I'm going to do right away. 22 Celsius is 295 Kelvin. So we're going to substitute our values in. So 97 kilopascals, 97 kilopascals. This is my initial pressure, and this is my initial temperature. And the tank gets up to, it got at least up to, or not, sorry, at most up to this pressure, P2. So now we're trying to find what the maximum temperature it could have reached. So T1 is 295 Kelvin, and P2 we know is 350 kilopascals, and T2 we don't know. So this is where the algebra takes a bit of a turn because lots of times students will just move the 350 over and say, I'm solving for T2, it's all by itself on one side. But if you move the 350 over, maybe I'll even just show this for a second. So you would divide, because the 350 is in the numerator, so I would move it over and it'd be in the denominator, so I have to divide both sides by 350 kPa. 350, don't write this down. But if you did this, now this is gone, that leaves a 1 there. So when you solve this out, you're actually going to get 97, I'm just going to read the numbers, 350, 295 equals 1 over T2, and that's not what we're looking for. That's the opposite of T2. That's the inverse of T2. So that would be incorrect algebra. We need to get T2 out of the denominator first. So I'm just going to rewrite this. So we start off with 97 kPa, 295 Kelvin equals 350 kPa over T2. So when we're solving for a temperature, the algebra is important. The first thing we got to do is get T2 out of the denominator. It's buried right now. We got to get it out. So I'm going to multiply both sides by T2. These cancel. So what ends up happening is you get 97 kilopascals times T2. I switched them there, but it doesn't make a difference. Over 295 Kelvin equals 350 kilopascals. So now we need to solve for T2. To get rid of the 295, it's dividing now, so I'm going to multiply both sides by 295 Kelvin. So that would cancel these. And then I'm going to divide both sides by 97 kilopascals. These would cancel. So I'm going to rewrite what we have here so you can see what happens after we do those two steps. T2 would equal 350 kPa times 295 Kelvin over 97 kPa, which is actually the inverse of what I had when I did the algebra wrong. So now we set that up. You should get a value of T2 being 1064 Kelvin. Now, if you did the algebra wrong, you would actually end up with a temperature that was lower, and that would tell you that you did something wrong. Remember, this is going through a fire. The pressure is rising. The temperature should be bigger, so you should get a bigger value. Now, the question did ask us, or it didn't ask us for the temperature in Celsius, but if you wanted to, if it doesn't ask you, you don't have to, but if you wanted to change it to Celsius, that would be fine as well. So we'd take away 273, and it would be 791.4 degrees Celsius. Now, if we're doing this logic method, there's less worry about the algebra because we're just using ratio. So in this case, the pressure has gone up, so we got to make the temperature go up. So I'm going to take my temperature, 295 Kelvin, and we're going to multiply it by the pressure ratio that makes it get bigger. So 350 kPa on the, 350 kPa over 97 kPa. So now we do that math, and you still get 1064 because it's the same math, and then we could change that to Celsius if you want. So this is where the formula method becomes a little bit more difficult in the sense that you have to know how to do that algebra. Again, those are skills that you will definitely need in science. So I would argue that you should be able to do those things as well. But in our course, our focus is just on the relationship. So I'm okay with using the ratio method. But definitely those math skills are skills that you will need to continue on in science. Let's move on to the next one. And this one we are looking for new pressure. So we don't have to worry about the algebra so much. And actually all the temperatures are already in Kelvin for us, so we can just set this up. So P1 over T1 equals P2 over T2. So P1 is what we're starting off here, and T1 is here. Now notice like these end up being P1, T1, and then whatever. You have to really read the question and make sure if you're using formula method that you're putting things in the right places. The cylinder is heated up to 400, so that's T2. We want to find the new pressure at 400. That's still T2. So lots of times I'll find students, they see 4 numbers there and like, I don't know what to do. I've already got all 4 numbers. Well, actually, we only have 1, 2, 3 numbers. It's just repeating the number once. So now we're going to set those values into our equation, 125 kPa over 300 Kelvin equals P2 we don't know, T2 is 400 Kelvin. So now to solve for P2, we're going to multiply both sides by 400. So P2 equals 125 kPa times 400 Kelvin divided by 300 Kelvin. So P2 should equal 166.7 kPa. If we're doing logic, the temperature rises, so the pressure also must rise. So I'm going to make the pressure get bigger. So I got 125 kilopascals. I want to make it bigger. So the bigger temperature on top, smaller temperature, 300 Kelvin on the bottom. And that's the same math, and I get 166.7 kPa. So a lot like Charles' law. It's actually the same relationship, just dealing with pressure instead of volume. And again, notice for all 3 relationships, we held the amount of gas constant. For Boyle's, we hold the pressure, we change the pressure into volume and we hold the temperature constant. For Charles, we change the temperature and volume and we hold the pressure constant. For Gay-Lussac's law, we change the pressure and temperature and we hold the volume constant. We have a rigid container. So that's how we got these 3 relationships in the first place. And then our next step that we're going to be doing is we're going to actually take all 3 and combine them so you could actually have more than one thing changing at a time. So let's say you heat something up, but the container expands, but the pressure also increases because the container doesn't expand frictionlessly. We can actually calculate what that new volume should be, which actually would have been good for our Charles' law lab. Okay, so that'll be the end of Gay-Lussac's law.